Welcome to another lecture in the course Python and Matrices. In this lecture, we will focus on main concepts related to eigenvectors and eigenvalues. So let's get on with it. So what are eigenvalues and eigenvectors? Essentially, eigenvectors of any linear transformation, which in this case will be essentially a matrix, is a non-zero vector that changes by a scalar factor when the linear transformation is applied to it. Okay. So when we are talking about eigenvectors, when we are applying the transformation, which is essentially multiplying that vector by a given matrix, then that after transformation, that vector is essentially going to stretch or squares by staying on its own span instead of changing the direction. And what is the span? Span is essentially the initial line that is passing through its tips and the origin. So let's get through the geometrical concepts and geometrical intuition about what we are talking about and what is listed here in this slide, what we mean by span, what we mean by stretching, and what we mean by transformation, and how that concept is related to eigenvectors and eigenvalues. Okay. So here, let's consider three different vectors. For example, the vector 1, v1, which is located at square bracket minus 4, 2. Vector 2, which is located at square bracket minus 1 and 2. And vector 3, which is located at minus 2 and 0. Okay. So these are the three initial vectors that are basically depicted in the diagram that you see right now. And let's say if we apply a linear transformation to it, which essentially means that if you multiply these vectors by 2 by 2 matrices, then what can happen? Okay. So there are many scenarios that is possible, but by applying a transformation or by multiplying these vectors by a given matrix, for example, let's consider this matrix, which is, for example purposes, if I have a matrix 2, 2, 0, 1, which is multiplied to each of these vectors, one of the things we know that what transformation does or what a matrix multiplication does, it basically transforms and shifts the vectors to a different location, or it stretches them, right? So what we'll see that after applying this transformation will basically change the location and the orientation of the unit vectors, and it will also transform the vector to which this matrix is multiplied. But after applying this transformation, if you look into the transformed unit vectors, which is transformed I, transformed j, they have changed the location. If you look into the previous diagram, the I was in this direction, j was in this direction, but since we are doing this transformation, this I and j location is going to change, and it's essentially the transformed I is going to be along this direction and transformed j is going to be along this direction. Now if you go back to this diagram here and look at what happens to the individual vectors v1, v2 and v3 after the transformation, that will give us the geometric intuition behind what we mean by eigenvectors. So let's take this transformation and let's see. So if you look from previous, the vector v1, it did not change its direction even after the transformation. It's essentially lying along the same span, or essentially lying along the same line where the previous case, where our tip, if you look into this vector right here, this is the tail, this is the tip, and after transformation v1 still remains at the same thing. So in fact it did not even stretch, it has the same size. Now let's look into vector 2. So the vector 2 is here, and once we applied this transformation on vector 2, which means that we took this matrix, multiplied this matrix by this vector, and that changed the location of the vector, because that multiplication will essentially result in 2, 2. So that's how that second vector gets transformed. And as you can see, this second vector is in a completely different direction than what v2 was. It's not along the same direction. It is in a completely different direction after transformation, right? Whereas if we look into the case of v3, which is originally here in this direction, so this is the tail and this is the tip, so this is the general direction, this is the span of v3, and if we did the transformation by this matrix itself, you will see that v3 has stretched. It has become in fact twice the original size, but the span or the direction of this vector has not changed. So out of the three vectors that we transformed using this transformation matrix, we see that V1 and V2 maintained their span. V1 did not stretch or shrink, but V3 stretched, whereas V2 essentially changed its direction. So this is the geometric meaning where V1 and V1 and V3 are originally along this original span, and they are not changing direction. And these vectors, which even after transformation do not change they lie along this original span, they are known as eigenvectors. Whereas the vectors which change their span and they change their direction after transformation, they are not called the eigenvector of the transformation. So with this example, the geometric meaning and the intuition is, before and after, if you look into vectors V1 and V3, they did not change their span, and they essentially stretched or remained the same even after transformation. And these vectors which remain along the same span and do not change their general direction, they can stretch and deform and extend, but they do not change the direction, are known as the eigenvectors corresponding to the transformation matrix that we have. So the eigenvectors and eigenvalues are associated with the transform matrix. So far we understood the concept of eigenvectors. Let's deal with the idea of eigenvalues. So summarizing, you can see that V1 and V3 does not change the direction. They are just scaled with some factors. This one was remaining the same. This one was scaled by twice the factor. And those vectors which have these properties after transformation are known as eigenvectors and eigenvalues. Okay. So again, any other vector on these two lines are just scaled by some factor and hence remains its own span. And this is what is known as eigenvector of the transformation. So in this case, you will see that 1, 0 and minus 2, 1, right? They are essentially the eigenvectors of the matrix which was listed here, which basically gives us the transformation. So those two vectors are eigenvectors of the matrix, transformation matrix, which is listed here. Okay. Now let's also look into what we mean essentially by the eigenvalues. So far we know the eigenvector concept, but also geometrically understand what is the eigenvalue, right? Now the factor by which the eigenvector is scaled, which is it is extended or compresses or becomes smaller, is known as the eigenvalue after transformation. So let's look in the same example, and you will see in this example what is happening after transformation. The V1 vector that we have, that V1 vector is essentially remaining the same. So it's essentially getting stretched by a factor of 1 because it is not changing its magnitude also, right? So this is essentially a factor by 1. Whereas in the case of V3, we will see that after transformation, the V3 stretched and the magnitude of V3 became twice. So this is stretched by a factor of 2, right? So these are the two eigenvalues corresponding to V1 and V1. So what we'll say that eigenvalue of 1 is related to eigenvector V1 and eigenvalue of 2 is corresponding to the eigenvector V3 that we have. So those are the two eigenvalues that we have, lambda 1 and lambda 2, and these are corresponding to V1 and V3, and that is the concept of eigenvalues with respect to geometric intuition. So essentially the factor by which the eigenvectors compresses or extends is essentially represented by the magnitude of the eigenvalues that we have.